All right, so picture this. You're trying to take a picture, but not just any picture. You want to capture a hummingbird's wings frozen in mid-flap. It's got to be like the perfect shot, right? Well, that's kind of the challenge these physicists tackled. Except instead of birds, they were dealing with electrons.
And fast doesn't even begin to describe it. Imagine trying to measure something happening in attoseconds.
Yeah.
It's like comparing 1 second to the entire age of the universe. That's how quick we're talking.
Okay, I think my brain just melted a little. So how do you even begin to observe something that's gone in a flash like that? It'd be like, I don't know, studying a lightning strike with a 1-second exposure time.
It's all about having a fast enough camera shutter. And for a long time, the best we had were lasers. Even the fastest lasers could only work on the femtosecond level, though. A millionth of a billionth of a second. Helpful, sure, but nowhere near quick enough to catch these electrons in action.
So how did these Nobel Prize winners, Agostini, Krausz, and Lhuillier, finally crack the attosecond barrier?
It all began with Anne Lhuillier. She was working with lasers and noble gases. And she discovered that if you shoot infrared lasers, which, by the way, have longer wavelengths and lower energy, through these gases, you can actually generate something similar to musical overtones, but with light.
Okay, hold on. You're going to have to break that down for me. Light with overtones. That sounds like something straight out of a sci-fi flick, honestly.
It does, doesn't it?
Yeah.
But think about it this way. How does a musical note actually work? You have the main frequency, the note itself, but then on top of that are all these higher frequencies called overtones or harmonics. They're what make a middle C on a piano sound completely different from a middle C played on a guitar, even though it's the same note.
Ah, okay, that makes sense. So you're saying light can have these, like, tonal variations as well.
That's exactly it. What Lhuillier discovered was that the overtones of light produced by these lasers and noble gases, they had way shorter wavelengths, pushing them right into the ultraviolet spectrum. And that was the key. That's how they could finally capture these crazy fast processes, like electrons move.
So we've got our high-speed camera flash now, these super short ultraviolet bursts. But how do they actually let us see what an electron is doing?
It all comes down to how light interacts with the atom itself. Imagine the atom's electrical field is like a well, and our little electron is trapped at the bottom.
All right, I'm with you. Our electron is stuck, hanging out at the bottom of the well.
Now imagine a powerful laser pulse comes along, and it totally warps the shape of that well, creating this sort of escape tunnel. It's like a prison break for the electron. Quantum tunneling is what it's called.
Whoa, that's wild. So the electron just, like, tunnels out. Does it just disappear?
Not quite. It escapes the well, but it's still moving within this intense laser field, right? And as it moves, it's absorbing energy from the field. Think of it like the electron is on a roller coaster, just soaking up the energy.
Okay, got it. The electron's on this wild ride, but then what?
Well, every ride has to end, right?
Yeah.
The laser field eventually shifts and yanks the electron back towards the atom's nucleus.
So much for our electron's big adventure.
Not so fast. It wants to reconnect with the nucleus, but remember all that energy it picked up. It can't reconnect unless it dumps that extra energy, and it does that by emitting a flash of UV light.
Wait a minute, that flash of UV light, that's the overtone. That's how we're seeing the electron.
You got it. It's like the electron is leaving behind a trail of breadcrumbs, showing us exactly where it's been and how much energy it snagged along the way. And since this all happens so insanely fast on the attosecond timescale, those flashes are incredibly short enough to give us a glimpse of the electron's movements.
So we're actually seeing the energy burst of a single electron as it's pulled back to the nucleus? That's unbelievable.
And we're just getting started. That was just Lhuillier's breakthrough, remember? Next time, we'll talk about what Agostini and Krausz were able to do with it.
There's more. This is already blowing my mind. So last time we were talking about Anne Lhuillier's work generating attosecond pulses, those ultra-fast flashes of UV light. It's like having a strobe light, but for the world of electrons.
Yeah, a strobe light that freezes action a billion times faster than any normal camera.
It's pretty incredible when you think about it, but actually getting those pulses, that was only the first step, right?
Yeah.
What did the other Nobel Prize winners, Agostini and Krausz, do?
Okay, so imagine those attosecond UV flashes we talked about, but not just one. It's more like a constant stream firing, one after another, kind of like a pulse train, where each pulse is like a single car on that train.
Yeah.
And that was Agostini's big contribution. He figured out how to generate these attosecond pulse trains.
Okay, I think I get it. So it's like a whole line of attosecond pulses, but wouldn't that be like taking a burst photo with a camera? You get all these images, but they're all kind of blurred together.
That is a great way to put it.
Oh.
And you're totally right. For a lot of experiments, You don't really want a whole train of pulses. Sometimes you just need one single attosecond pulse, one super precise snapshot to analyze, and that's where Ferenc Krausz comes in. He's the one who figured out how to isolate a single attosecond pulse. It's like he found a way to detach just one of those train cars from the rest of the train.
Wow, so he basically created an attosecond camera shutter. That's amazing. What kind of things can we actually see with that level of precision?
Well, one of the first things scientists wanted to figure out was how long it actually takes for an electron to escape from an atom. Before this, we just kind of assumed it was instant.
Because it happened so fast, we never had the tech to even measure it, right?
Exactly. And with attosecond pulses, we can actually time it, and it turns out it's not instant at all. The speed actually depends on how strongly the electron is bound to the nucleus.
So like an electron in a smaller atom, it would take longer to escape because the nucleus has a stronger pull.
Yeah.
Kind of like comparing how easily you could break free from a bear hug versus a loose handshake.
Yeah, exactly. That's a perfect analogy.
Yeah.
But that's just one example. Attosecond pulses also let us study how electrons act inside molecules. Before, we could only get like a still image, an average of where the electrons were. It's like trying to figure out what a hurricane is doing just by looking at the average wind speed for the day.
You'd miss all the details, the way the wind actually swirls and changes the real dynamic stuff.
That's right. But attosecond pulses actually let us see these things called electron clouds oscillating inside molecules, and we can see it all happening in real time. So we can see how these clouds change shape and shift around instead of just this blurry average picture. It's like going from a blurry photo to a high-definition video of what's happening at the atomic level.
That's incredible. It's like we can watch electrons dance, so that's amazing. But this is getting kind of abstract. Are there actual real-world applications for this attosecond technology?
The possibilities are basically endless. Think about electronics for a second. Imagine if we could build circuits that run at attosecond speeds.
We'd be looking at a revolution in computing power.
Exactly. Attosecond tech could completely change everything from how we store data to how we communicate to how we produce energy. And it's not just about speed either. Once we understand how electrons behave at this level, we could create entirely new kinds of electronics using principles we haven't even thought of yet.
Okay, so that's super fast electronics. What about other areas? You mentioned something earlier called molecular fingerprinting. I've been dying to hear more about that.
Now that is where things get really interesting.
Last time, we were in the middle of this whole world of attosecond pulses, watching electrons zoom around. It's like a high-speed chase, but on an atomic scale.
And we're not just watching anymore either. Attosecond tech is letting us figure out how to control those electrons, maybe even manipulate their movements.
You were about to explain this thing called molecular fingerprinting, right? Before we wrapped up last time. It sounds like something right out of a science fiction movie.
Right. It's pretty wild. So imagine you shine an attosecond laser pulse onto a molecule. That pulse interacts with the electrons in the molecule. And as we talked about, those electrons emit a burst of light as they go back to their ground state.
Right, those little breadcrumbs of light showing us where the electron's been.
Exactly. But here's the thing. That burst of light, the specific pattern and energy of it, it's unique to that molecule, like a fingerprint.
Hold on. You're saying every molecule, from water to DNA, they all have their own unique attosecond fingerprint.
That's the idea. And we're just starting to figure out what we can do with it. Imagine being able to identify any molecule in a snap, like instantly spotting pollutants in water, or even detecting diseases super early on, all by analyzing their light signatures.
So this could revolutionize medical diagnostics. That's huge.
It's definitely possible. This technology is still young, but the potential is mind-blowing. We've gone from not even being able to see electrons move to watching them in action. And now we're on the verge of controlling them, like choreographing their every move.
It's kind of amazing and terrifying all at the same time. This whole deep dive has been incredible. It's like my understanding of, well, everything has been flipped on its head.
That's what attosecond science does. Makes us rethink the universe from the ground up. And it reminds us that the most important discoveries, they can come from the tiniest places.
I can't wait to see what's next for this field. But that's all the time we have for today's deep dive into attosecond physics. We'll be back next time with another fascinating topic. Until then, keep exploring.